Hi! Today we're going to discuss basics of rectilinear perspective. And first of all, let's find its origin in real world. Because rectilinear perspective not always looking natural to our brains, some people may think that it's just an artificial invention and has nothing to do with reality. But it has. Let's take a look at a pinhole camera. It's a simple camera without the lens but with a tiny aperture, a pinhole. Effectively a light-proof box with a small hole in one side. Let's draw it. Well, this is our box. Let's draw through. Tiny aperture and some small object. It could be a candle. Light passes from an object through the pinhole and projects an inverted image on the opposite side of the box. Imagine that this is light rays. One more, and we get our inverted image. This effect, also known as camera obscura. The difference is that pinhole camera do not have a lens. That's why the rays do not bend, and we get ideal rectilinear perspective. Also, it has infinite depth of field, which results in equal sharpness of all objects in photograph, regardless of the distance. Our eye has a lens in it, so we see in curvilinear perspective. But it's not a problem. Brain could interpret any kind of perspective. Well, with that said, let's see how projection of light rays or visual rays method works. I'm drawing a line which will represent both horizon line and picture plane, station point and line of sight, and we need a simple object. Let's draw a perfect cube. This is our cube from the side, and this is from the top. And now we're going to connect these points to station point. And one more. We could project height of the cube, width of the cube. From this corner, we would go to center of vision. Because these lines are perpendicular to our picture plane. And now the question is where this face ends in perspective. Well, we need these intersections, and from there we would go straight down like this, and this is our face in perspective. Okay, let's do it from bottom one. Here. And we got our perfect cube in perspective. Let's darken it so we could see it better. Okay, now I want to bring up another simple concept, which is all problems in perspective you could solve out of perspective. For example, finding depth of the top face of the cube. Well, let's pretend that we don't know where this face ends in perspective. How we could find it? Okay, let's look at the top square, at this cube from the top, and we see that this angle equals 45 degrees. So if we could draw 45-degree diagonal in perspective, we could find this intersection. Well, let's do it. From station point, we go 45 to the right, 45 to the left. On intersections, we would find VP 45 here, vanishing point 45 here. And now we could draw lines going from these corners to vanishing points. And you could see that it matches exactly with our previous construction. Let's do it for bottom one. Okay. And now you can see that 1 and 2 point perspective is the same rectilinear perspective, just with different angles. And talking about angles, let's draw 2 point perspective and understand distortions better. Okay, let's start with horizon line. Station point line of sight, 45° to the right, 45° to the left, finding our vanishing points, station point, and center of vision. Now let's draw a couple of boxes. Some of them would be near center of vision, and some of them would be far away. Like this. One more here. Oh, sorry. Go into vanishing points. One more here. And another right here. Okay, do you remember 60-degree cone of vision from the previous lesson? Well, let's draw it. Approximately 30° to the right from station point, 30° to the left. And now we could draw cone of vision that is 60°. Okay. And you could see that the boxes that are inside of 60-degree cone of vision, they are less distorted, and ones that outside of it are more distorted. So if you crop your final image something like this, in this range, it will look natural. However, if you crop it too small, like this, the perspective could look shallow, so you could vary it based on your intent. Okay, the next thing is measuring. There are too many ways of accurate measuring in perspective for one lesson, so I will concentrate on few of them. First of all, it's measuring points, and probably is the most important tool in terms of accurate drawing in perspective. Well, let's start with drawing 2-point perspective perfect cube and rotate it 30 degrees relative to us. Okay, station point, 30 degrees to the left, 30 degrees to the right. Finding our VP 30 here and VP 60 here, center of vision, station point. Now let's assume that this is our height, and let's draw a perfect cube. This is height of the cube, and we know that height of the cube and width of the cube is equal, so are equal. So let's do this. Really, if you do it traditionally, it's easier to do it with ruler. Now I'm just using square for transferring it equally. Okay, now we need to find measuring points. How are we going to do that? Let's take this section and rotate it, or you could say swing it up to horizon line. This is our first measuring point, and let's do it with this one. This is our second measuring point. And there is another way to find these. You could draw bisector of this angle, you see, or this angle, or you could rotate it or measure the length of this section. This is measuring point 60 and measuring point 30. Now, we should connect this to measuring point 60 from here to measuring point 30. And on this intersection, we could draw face of our cube from this corner to VP 60 and to VP 30. Let's draw through. Okay. And we got our perfect cube. Okay, this is perfect cube using measuring points. And you could use not only 1 by 1, but 1 by 2, 2 by 4, whatever you want, whatever you need. Okay, next thing is diagonal vanishing point. Often used for quick drawings of squares in perspective. Let's start with our horizon line. Drawing station point, line of sight, 30 degrees to the left, 60 degrees to the right. So it's not going to be symmetric. Okay, like this. Now, let's draw. Imagine that this is a floor, and we want to make it with squares. Okay, this is VP 30, VP 60, station point, center of vision. Okay, and now we want to know where this ends to be a square. We could bisect this angle. And by the way, let's look how it works. Out of perspective, we could draw a square and draw another square. And diagonals of these squares would be parallel to each other. If they are parallel, so they would converge on the same point in perspective on the horizon line. So we could, and you see it's a bisector of this angle. So we could bisect this right angle in perspective like this, approximately, and find our diagonal vanishing point. Okay, now we could connect this corner to diagonal vanishing point, and on intersection we could find our perfect square in perspective. I know it's very distorted because I want to draw very big for this construction so you could see lines better. Okay, and we could do one more. To diagonal vanishing point goes here, and to diagonal vanishing point goes here. Now if I outline it, you could see that they are identical and equal in perspective, and these diagonals go to same vanishing point, diagonal vanishing point. Okay, next thing is distance point. You could use this type of construction for any groups of parallel lines. So let's imagine that you could have the pattern on the floor with first narrow rectangle, and after that more wide, and one more narrow and wide. Diagonals of these rectangles would be different, but these ones parallel and these ones are parallel. So we got 2 points, 2 distance points, and you could call it special point. Okay, let's draw one narrow square and draw a diagonal to the horizon line, like this. This is our distance point 1. And let's do the same thing for this one. This is our distance point 2. Okay, now we could just go from here to distance point 1, distance point 1, and get our narrow. And from distance point here, go to distance point 2, got our wide one. And last one goes to the narrow. You know, it's very difficult to make it accurate on a tablet and quickly, but I think you get the idea that you could draw any pattern on the wall or on the floor, and you could use diagonal vanishing points or distance points for your purposes. Okay, next thing is dividing in perspective. Remember that we could solve every perspective problem out of perspective. Well, if we have, let's say, this narrow rectangle and we want to duplicate it exactly here, okay, we could use our distance point, right? No problem. Okay, but we could use also geometry, simple geometry. Like we have a rectangle, and we could find dead center of this rectangle, like this. This is center. Draw horizontal through the center. And now if we draw from this corner through the center, we would find same rectangle as this one. So we could do it in perspective. We have first diagonal, second diagonal. This is our center. And now we could draw through the center here and find our copy or next rectangle that is equal to this one. We would discuss more advanced dividing methods in later videos. And for today, the last one, it would be inclined planes. Okay, let's start with our horizon line, station point, line of sight, 45 degree to the left, 45 degree to the right. This is our VP 45, and you could call it left vanishing point, right vanishing point, whatever you want. It really doesn't matter. Station point, center of vision. Okay. And let's draw a house like this. A little longer on this side. Okay, and we want to draw a roof. Like this is our house, and we want to draw a roof like this. Okay, we could do it just very easy, vertical through the VP 45, and anywhere where this line intersects, the next one would be convergent. Okay, no problem. But what if we want to make it with specific angle? Well, we need measuring point. Let's find it with bisecting this angle. We find measuring point 45 degree, and this angle, this one, represents the angle of the roof in perspective. Okay, let's choose this one, and on intersection we got ascending vanishing point, or you could call it whatever you want. From this corner we go to vanishing point, from this to new vanishing point, and if you want to make it symmetric, we could divide this with diagonals, or we could choose it just where we want, like this goes here, and we got our house. Let's darken it up. Okay, that is for today, and this construction led us to the next lesson on three-point perspective and more advanced methods. If you are interested, please subscribe. Any questions in the comments below, and thank you. Bye.